Welcome to the second part of our discussion on memory, Module 23, Storing and Retrieving Memories. What is the capacity of our long-term memory? Are our long-term memories processed and stored in specific locations? Theoretically, our capacity for storing long-term memories is essentially limitless. This is contrary to the belief that we can fill more items only if we discard old ones. When it comes to retaining information in the brain, if information is not stored in a single precise location in the brain. Memories are brain-based, but the brain distributes the components of a memory across a network of locations in the brain. Some of the brain cells that fired when we experience something fire again when we recall it. Despite the brain's vast storage capacity, we do not store information as libraries store their books in single precise locations. Instead, brain networks encode, store, and retrieve the information that forms our complex memories. And if we were to look at this from a efficiency perspective, if we had to retain a piece of information about something we might learn every single time, we might actually fill up that information. So therefore, every time we learn about a new car, if we had to remember the concept of wheel, that would be very inefficient because we already know what a wheel is, and that's stored in part of the neural network. So what are the roles of the frontal lobes and the hippocampus in memory processing? We have two conscious memory systems, our semantic memory, which is our explicit memory of facts and general knowledge, and our episodic memory, the explicit memory of personally experienced events. The hippocampus is a neural center located in the limbic system. It registers and temporarily holds elements of explicit memories before moving them to other brain regions for long-term storage. The neural storage of long-term memories is called memory consolidation. Explicit memory system, the hippocampus. Explicit memories for facts and episodes are processed in the hippocampus, the orange structures, and fed to other brain regions for storage. What are the roles of the cerebellum and basal ganglia in memory processing? The cerebellum plays an important role in forming and storing implicit memories created by classical conditioning. The basal ganglia, a deep brain structure involved in motor movement, facilitate formation of our procedural memories for skills. Infantile amnesia involves conscious memory of the first 3 years, which is blank. The command of language in well-developed hippocampus is needed in order to have memories formed at these ages, and the hippocampus is one of the last brain structures that actually matures. How do our emotions affect our memory processing? Excitement or stress triggers hormone production and provokes the amygdala, two limbic system emotion process clusters, to engage memory. Emotions often persist with or without conscious awareness. Our emotional arousal causes an outpouring of stress hormones, which lead to activity in the brain's memory-forming areas. Flashbulb memories are clear memories of emotionally significant moments or events, and they occur via emotion-triggered hormonal changes and rehearsal. This is a review of the key memory structures in the brain. The frontal lobes and the hippocampus are involved with explicit memory formation. The cerebellum and basal ganglia are involved with implicit memory formation, and the amygdala is the emotion-related memory formation. And amygdala is actually Greek for almond, and they're like almond-like structures on either side of the brain as part of the limbic system. How do changes at the synapse level affect our memory processing? We talk about long-term potentiation. This is an increase in the synapse firing potential after brief, rapid stimulation. After LTP, brain will not erase the memories. It is believed to be a neural basis for learning and memory. Kendall and Schwartz observed synaptic changes during learning in the neurons of the Californian sea slug, Aplysia. Their research pinpointed changes in sea slug's neural connections. With learning, more serotonin is released and cell efficiency is increased. The Aplysia is the California sea slug, which neuroscientist Eric Kandel studied for 45 years, and it has increased our understanding of the neural basis of learning and memory. We have double receptor sites, and this electron microscope image shows just one receptor site, gray, reaching toward a sending neuron before long-term potentiation. Image B shows that after LTP, the receptor sites have doubled. This means that the receiving neuron has increased sensitivity for detecting the presence of the neurotransmitter molecules that may be released by the sending neuron. In this flowchart, we look at the specific memory systems that we have. On the left in the blue, we have our automatic processing. These are implicit memories, non-declarative, without conscious recall. They are processed in the cerebellum and basal ganglia, and they are impacted by space, time, and frequency, such as where you ate dinner yesterday, your motor and cognitive skills, such as riding a bike, and classical conditioning, such as reaction to a dentist's office. On the right, we have effortful processing, which includes our explicit memories, our memories of facts, with conscious recall. They are processed in the hippocampus and frontal lobes, and they include semantic memory, our facts and general knowledge, such as this chapter's concepts, and our episodic memory, our personally experienced events, such as family holidays. How do external cues, internal emotions, and order of appearance influence our memory retrieval? Memories are held in a storage by a web of associations. The retrieval cues serve as anchor points for pathways to memory suspended in this web. When you encode into memory the name of the person sitting next to you in class, you associate it with other bits of information about your surroundings, such as your mood, the seating position, and so on. The best retrieval cues come from associations formed at the time a memory is encoded. Priming is the activation, often unconsciously, of particular associations in memory, and this helps us with retrieval. What's interesting is one of the most powerful cues for memory are smell, and taste as well, because they typically are very strong senses because they have to do with our survival. And we look at memory retrieval or retrieval cues, we have a priming, which is awakening the associations. After seeing or hearing rabbit, we are later more likely to spell the spoken word hare as in H-A-R-E, and the associations are unconsciously activated by these related associations. This is the process of priming. Context-dependent memory involves improved recall of specific information when the context present and encoding and retrieval are the same. Cues and context specific to a particular memory will be most effective in helping recall of that information. State-dependent memory depends on our emotions and that accompany good or bad events that become retrieval cues. Mood-congruent memory is the tendency to recall experiences that are consistent with one's current good or bad mood. In a bad mood, we may read someone's look as a glare and feel even worse. In a good mood, we may encode the same look as interest and feel even better. Passions exaggerate. And to finish this part of the module, we talk about the serial position effect. This is our tendency to recall the best and last items in the list, the last being called the recency effect and the first being called the primacy effect. So if we look at these two lines, we will see the one on the far left talks about the later recall, and only first items are recalled well, and you see the blue line drops very quickly based on the position. And then if we look at the last words in the list, or the recency, which is the pink or orangish line, at the end of the list, the line is much higher, which means a higher level of recall.